Hi everybody. Okay, let's go ahead and get started. We're going to talk about the derivative as a rate of change. So we've been saying a lot of things about derivatives lately, mainly how you can interpret them. And in this section, it's going to basically be how you use them in certain like real life problems. So it's not a very long section, but it is pretty interesting. A lot of times it has to do with functions like when you're interested in like maybe throwing something, or it could honestly be a function that describes anything, but a lot of times it has something to do with throwing an object or something falling. Often is when you see these types of problems. But let's get right into it. So the derivative as a rate of change. Okay, let me switch markers. This one's already no good. Okay, so we've talked about derivatives already, but let me give you this new way or definition. It's actually something we've already kind of talked about for derivatives. So the instantaneous, I always pause on this one, instantaneous, there we go, instantaneous rate of change. The instantaneous rate of change of some function, we're going to call it f, with respect to, so WRT is with respect to x, and this is at a particular value of x, we're going to call it x naught, is the derivative. So is the derivative, which is f prime of that x value, x naught, which our limit definition is the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h, provided this limit exists. Provided this limit exists. Okay, so this part is not new. We've seen this same thing for a while. We keep talking about it. When someone says, what's a derivative? You can say it's the instantaneous rate of change. It's how something is changing at a particular instant, and the something is a function. And usually the function, it's going to be given to you in terms of like what functions usually look like f of x equals something. But the function can describe a lot of real life situations. And that's what's going to happen. We're going to go through an example in this section with the real life situation here. So we've seen this before. You now actually know some shortcuts using all your differentiation rules. There is a power rule, product rule, quotient rule, constant multiple rule. But this is the formal definition for a derivative, even though you know all the shortcuts now. All right, so now what we're going to talk about is motion of an object. So if something is moving, okay, so motion of an object, and we want to specifically look at it along a line. So this object is moving in a straight line path. Maybe you're pushing, I don't know, a cart down an aisle of the grocery store. Okay, a motion of an object along a straight line path. The position can be our function. So the position of that object is our function f. We can call it f of t. I know up here I have x, but a lot of times when you're applying these functions to real life problems, we tend to use t, and one reason is for t to represent time. Like after 2 seconds, where is my object? So f of t represents the position of the object. Then the displacement, and this is, I'll be specific here, of an object over time t, we'll say to t plus delta t. Let me explain that part. So displacement, how far did that object actually move from where it started? So you have a starting time, a starting t, and this is saying you're ending t, because this is the change. When you see delta in math, the capital delta like this, it means change. So it's this t value plus the change in that t value. So for example, let's say I started at 0 seconds. Maybe this is plus 3 seconds later. So 0 plus 3 seconds. And so let me write it up here so we have some room. And then I'll draw a small image for you on this. Okay, so our instantaneous rate of change is our derivative of our function. So that displacement, you can say is the change in f, okay? The change in the position. That's one way you can talk about displacement. And that's just f of t plus delta t, your ending position, minus your starting position. Okay. Hopefully that's pretty straightforward. If this is just saying if this represents position, this is where I'm stopping at, minus where I started at. This is the difference. So that's like what my object traveled. And so the image, just a straight line path. This is my starting point, f of t. And then this is where I stopped, f of t plus delta t. And then the displacement is in between here. Let me change the color for us. So this is our displacement right in here, delta f. Okay, so that's just this idea. Okay, let's see. So let me give you the average velocity. Average velocity. And so velocity, you can think of that almost like speed. The thing is with velocity, it can be negative. And if you have a negative velocity, it just is indicating which direction you're going. Whereas speed would be positive no matter what. You usually don't say you're driving your car negative 20 miles an hour just because you turned around. So speed is always positive, but velocity, it can be negative. But think of them very similarly. So average velocity is just displacement over time. Displacement over time. And so that looks like delta f, the change in your position, displacement, over the change in the time. Okay. Well, that's actually just the slope of a line, okay? The slope of the function or tangent line at a point. Because if you remember way back from your algebra, the change in y over the change in x, that was your slope formula. That's essentially the same exact thing right here. And so we have, if you kind of just expand this, f of t plus delta t minus f of t all over delta t. This is like y2 minus y1 over x2 minus x1 because it's a change in the x's. So it's just your slope formula over and over again. And remember, derivative of a function, it's the instantaneous rate of change, but it's also the slope of your function at that point. It's the slope of the tangent line to your function at that point, but we go ahead and say that that's actually the slope of your function at that point. All right, so let's talk about this velocity idea a little bit more. So your velocity, I think, yeah, got that right, velocity, but instantaneous, so at a particular instant. Instantaneous. So your instantaneous velocity, we're going to use v to represent that. Real quick, any of you that have seen physics before, you probably already know this, but if you haven't seen physics or if you're going to go into it later, this will be good to know because you're going to talk about these things. So velocity, it's just based on all the things we wrote down here, the derivative of the position with respect to t. Okay, it's f prime if you want to say it like that. F prime of t. It's the derivative. It's the slope of the curve at that point or the slope of the tangent line at that point. And so our limit definition for derivative is just our limit as, this time it's going to be delta t goes to 0 of exactly what we just wrote right there. F of t plus delta t minus f of t all over delta t. So from our original limit definition for derivative, we basically just changed h to delta t. And then, of course, where we had x's, we're writing t's now. So putting this all together, we've learned the final formal definition for a derivative. It looks very much like this, just with h's and x's. We are now saying that that represents the instantaneous velocity of an object if your original function f represents the object's position. So putting that together again, if you know that your function, you're given a function or you found a function, if you know that function represents the object, some object's position in space, like where I'm at in an aisle in the grocery store with my shopping cart, or where the ball is in the air after I throw it, if I know my function represents position of some object, then when I take the first derivative, that actually represents the velocity of my object at that point. Okay? So first derivative of position is velocity. Now we're actually going to keep taking derivatives because it gets kind of interesting when you keep going here. So let's add to this. So what this says down here, let me just add it right down here. The derivative of position with respect to time is velocity. Okay, so that's what we wrote right here. All right, next one. Well, actually, before we do the next derivative, let me just clarify. I mentioned speed a little while ago. If you take the absolute value of the velocity, if you make sure it's not negative, then that's when we say it's speed. It represents the speed. So the absolute value of the derivative of your position function, that's speed, the speed of your object. All right, next is acceleration. Acceleration of an object. Okay, so I now know the speed or velocity of my object. Well, how much is it accelerating? Is it, let's say it's the ball in the air idea. If I throw a ball up, when it hits its highest point, it actually stops in the air. The speed stops, the velocity is 0, and then it starts to fall back down. And so there's moments when the acceleration is greater or less than what it was originally. So the acceleration is going to be represented by a. So velocity was v, acceleration is a. And this is the derivative of velocity with respect to time. Okay? Or you could say v prime if you want. So anytime I write this notation, feel free to write the prime notation, v prime. And because velocity was the derivative of position, that means if I just take my position function and I take the derivative twice, I differentiate it twice, I get acceleration. So this is the second derivative of position with respect to time. Okay, or you can call this f double prime if you want to use that prime notation. This is just my second derivative notation. So that's acceleration. When you differentiate position twice, you get acceleration. So I'll write that in just a second. But there is one more kind of interesting fact. If you take the derivative a third time, it's called jerk. Okay, so jerk is the change in acceleration. And so we could say j of t equals the derivative of acceleration with respect to time, which would be the derivative of, or the second derivative of velocity, but it's the third derivative of position. Okay, so if you want to, you can call this a prime, and this would actually be f triple prime. All right, so jerk is basically the change in acceleration. So like, let's say you're accelerating, kind of picture yourself in a moving vehicle, like you're in a car, and you're accelerating, but then you change your acceleration. Like let's say you're pushing on the gas pedal and then you let up all of a sudden, or you either push down all of a sudden. That change right there, that's called jerk. Okay, so we already wrote that the derivative of position with respect to time is velocity. So to sort of kind of put this all together, to summarize all these derivatives, if you have your position and you differentiate it, you're going to get velocity. If you take your velocity and you differentiate it, you're going to get acceleration. These are the ones you're going to see the most. We don't really deal with jerk a whole lot here in this class, but just so you're aware of it. If you differentiate acceleration, you get jerk. And so essentially you can get from position all the way down to jerk if you just keep taking derivatives. Okay, so that's the idea. We've learned about derivatives. We've learned how to compute them using our limit definition quite a bit. And then just recently we learned these nice shortcut rules, which we'll use pretty much from now on. Sometimes we'll go back to the limit definition. But as long as you now know that when you take these derivatives, what they represent, as long as your original function represents position, then you can apply these derivatives to real life situations. So let's go ahead and try a problem out. A question involving, this one's going to be a rock, throwing a rock. Okay, so example. A rock is thrown vertically, and we're going to throw it upward from a surface. Let's see. Actually, we're going to say upward from, let's see, the surface of the moon. Surface of the moon. And we're going to say at a velocity of 28 meters per second. And this reaches a height of, we're going to use, let's go with f of t, and it's 28t minus 0.8 t squared, that's a minus, meters in t seconds. Okay, so there's our question, well, our background, no questions just yet. We're throwing a rock vertically up, we're on the moon for some reason. Okay, so throwing the rock vertically up, and we know some stuff. Let me just highlight. So whenever you have word problems, if you're not in this habit, I recommend that you try it. Just underline things that you think are important, because you're going to have to refer back to them most of the time. So we know the velocity when we throw this rock up is 28 meters per second. We also know the height is this position. So height is the same thing as where my object is at in the air, meaning this is the position function. And then just so we know, time is in seconds here. All right, let's do a few parts to this. Part A, we're going to find the rock's velocity and acceleration at time t. Velocity and acceleration at time t. Squeeze that in there, time t. All right, so what does that mean? That means that when I answer part A to this question, I'm not going to get a number, because unless it's constant. So sometimes you have constant velocity, but I'm most likely going to get a function with t in it because I'm told at time t. I'm not told a specific time number, like 3 seconds, 5 seconds. I'm told at some random time t. So what I'm coming up with in part A is actually functions for velocity and acceleration. All right, so find the rock's velocity and acceleration at time t. So even though we were given this velocity here, this initial velocity, we are asked for a velocity function. So velocity is the derivative, and you can use, again, the prime notation, or you could say derivative of f with respect to t. But again, feel free to say f prime here. So velocity is the derivative of position. So I'm going to take the derivative there. And I'm going to use the power rule, since we learned it. You can still use the limit definition. You will get there. It's just a little longer. So power rule. 28t, the derivative of 28t. I'm going to go through this real quick, the long way with the power rule, just so you see it. But you technically have 28t to the invisible 1. So the power rule says I bring down that power, so 1 times 28, and then I subtract 1. Okay, so that's my first term. My second term, I have 0.8 t squared, but my power rule says I bring down that power and multiply, and then I subtract 1. So after you do enough of these, you're going to get really fast with these rules. So this is going to be 28 times t to the 0 minus 2 times 0.8, which is 1.6, t to the first power. And so if we just kind of make this look a little bit better, this is 28, because any variable to the first power is 1, minus 1.6t. And that's our velocity function. So just to write it right here, our velocity at any time t is 28 minus 1.6t. So we can plug in what time we're at, and we can find the velocity. And let's just verify. We know initially the velocity is 28 meters per second. And look, it makes sense. If I plug in time 0, my initial time, I get 28. So that's good. Kind of checks out. Then we were asked for acceleration, so we differentiate velocity, or take the second derivative of our position function. So acceleration is going to be the derivative of our velocity function with respect to t. And so the derivative of any constant is 0, so that's 0 for 28. And then 1 is minus 1.6. This is technically t to the first power. But anytime you have your variable to the first power, this is always going to happen, like what happened right back here. You're going to get t to the 0 when you differentiate any variable to the first power. So you can kind of skip that step and jump right into the fact that this turns into 1. So it's really 1.6 times 1, because this is your variable to the first power. So you can go ahead and just say that this is negative 1.6. And so your acceleration, I'll just write it like this, your acceleration at time t is negative 1.6. Technically, I could put my units on here. This would be meters per second squared. But notice there's no t here. So this is actually a constant acceleration. It's really decelerating because it's a negative, but it's a constant acceleration because I don't have a t. So it doesn't really matter what time I plug into this function. It's always an acceleration of negative 1.6. So let me just add those units on there. So this is meters per second, and this one is meters per second squared. All right, that's part A. Let's do part B. Part B is going to be to find how long does it take the rock to reach its highest point. So I'm going to go ahead and get rid of some of this up here, but hopefully we remember what we have. We have our position function. I'll leave that there. I know my initial velocity is 28, so I can kind of get rid of that. We'll leave our position right there. All right, so part B, how long does it take the rock to reach its highest point? How long does it take for the rock to reach its highest point? All right, we have to think a little bit to answer this one. So the nice thing, and I say nice because it actually makes us come up with our problem solving skills. The nice thing about word problems is you have to think about what you're doing and try to problem solve how to answer it. And here's what I'm saying. How long does it take for the rock to reach its highest point? Well, I'm not told, hey, just find the derivative. If that was it, I would just do the same work I did already. I'm actually having to figure out, how do I even answer this question? How do I find the answer to this question? So the highest point, what do I know about that? And so think about it real quick, and I kind of already talked about it a little bit earlier, but let's just kind of draw the path. Let's say I throw the rock up, and then it comes back down like that. Okay, so I threw the rock up and then came back down. its highest point right here. What can I say about this point? What do I know about that point? I know a few things. If I were to draw a tangent line to my path of my object, it would be horizontal, right there. I have a horizontal tangent line. The tangent line, the slope of it, is the first derivative of your function. Another way to say what I'm saying is the velocity is 0. Because any horizontal tangent line, the slope is 0. But if you think about it, if you throw something up, like I said earlier, it's going to stop right there as far as velocity. It's going to have a velocity of 0. It might speed up to get there and then be 0 and then speed up to go down. But right here at the highest point, your velocity is 0. So you have to come up with that in order to answer this question. So now that we know that, notice the question asks for how long, meaning that we want to know the time. So when the velocity is 0, what is the time? So let's go ahead and figure that out. So v of t, we don't know t, so be careful, don't put 0 here. We know the velocity is 0, so t is what we don't know. So 28 minus 1.6, t is 0. And then we just solve. So I'm going to add this term to the other side, so this is 28 equals 1.6t. And if I divide by 1.6, let's see, did I get this earlier? Let's just use the calculator really quick. And we get 28 divided by 1.6, 17.5. Okay, so we get 17.5, so t is 17.5 seconds. So after you throw the rock up in the air, 17.5 seconds later, it reached its highest point, and then it's going to start coming back down. Now, let's keep going. Let's try some more stuff. Let's see part C. How high does the rock go? We know how long it took for it to get to its highest point. So the question now is, well, how high did it actually reach? So part C, how high did the rock go? Or what was its maximum height is another way to say that. So again, problem solve. Think about it. How do you solve this? How high did the rock go? What do I know about its highest point? Well, from part B, I already know its highest point happened when the velocity was 0. And I've already done the work to find the time when that happens. So we've done half of the work here. How high? That is its position. That is its height. That's this function here. Remember, this was its height function or its position. Okay, so how high did it go? Meaning, what is f of t is the question. We know that it reached its highest point at 17.5 seconds, so we're just going to plug that into our position function or our height function. So we're plugging that right into our height function, and we're just going to simplify. 17.5 here and 17.5 there. Good. And this is just quick computation. Let's see, if you use your calculator and simplify, just go ahead and type that into your calculator, you're going to get 245 meters. Okay. So the highest that this rock goes when you throw it up is 245 meters. And you can say that in words if you want. I'm kind of just boxing them in, but you can always just say it in a quick sentence so you know what this represents. All right, let's keep going. Let's try another part. That was C. Part D. How long does it take the rock to reach half of its maximum height? Things are getting a little interesting here. All right, let's write that down. Part D. How long? So right away, I'm looking for time. How long does it take the rock to reach half of its max or maximum height? Okay. Now, do we have enough information to answer this question? Yes. because we've actually already done so much of the steps already. Okay, so let's say this was question A. If this was question A instead of D, we would have to kind of go through A, B, C without even being told to do those parts. But we have done all those, so we're ready for part D. Half the max height, well, from part C, we know we can just take half of this. So we want half of that number. So we're just going to say in the calculator, 245 divided by 2, 122.5. Okay, so we know that half of the max height is 122.5. And what do we do with this number? Well, how long does it take to reach that height? Again, this is a height. So we plug it in to equal this. It is the height, so it equals the output of our function. So this is 28t minus 0.8t squared. And we're just solving this. All right, so at this moment, it's just a lot of algebra. The height here equals our height function, and we're asked how long, so find t. All right, so let me jump into algebra real quick and think about it for a second. For algebra, go back to your skills you learned. What kind of equation is this? This is a quadratic equation. You have some options. You can try to factor it, you can try to complete the square, or you can use the quadratic formula. I would say quadratic formula. It's probably going to be the fastest because this is not the nicest numbers. So I'll kind of just guide you to it real quick and then we'll get that answer. So let's see, I think I can get rid of some of this. Let's take off this part. And for a quadratic formula, you want it to equal 0 to use that formula. So I'm going to have to bring over this 122. Or you can bring everything else left. I'm actually going to do that so I get a positive first term. So I'm going to add this term. I'm going to subtract this term. So I get 0.8t squared minus 28t plus a positive 122.5 equals 0. All right, so I'll just set up your quadratic formula with you, and then I'll give you the answer. So t equals negative b plus or minus square root b squared minus 4ac 122.5 all over 2a. All right, and then you just do these two separately because technically this is two answers, plus and minus. And so let's see, if we plug this into our calculator, I got the following. Okay, so you can try this out, and I got two answers. T equals, or is approximately, so T is about 5.13 and 29.87 seconds. All right, now let me see if you can understand this. Why was there two answers? I know, of course, because the formula has a plus and minus, so there's two answers that come out of the formula. But think about why this question had two answers. How long does it take the rock to reach its half of its maximum height? If we kind of redraw that really quick, let's get rid of that part. If I redraw this really quick, I have my rock getting thrown up and coming back down. Well, if its max height was here, think about it. It reaches half of that height on the way up and on the way down. That's why you have two answers. And the answers, they should kind of logically check out if you think about it. We knew that the max height happened after 17.5 seconds. Max height, 17.5 seconds. So one of our numbers should have been less than 17.5, and the other number should have been more, which it was. So this makes sense. So that's just sort of a quick logic check. Does my answers kind of check out? All right, let's see. I'm going to do one more part. Part E. How long is the rock aloft? Or how long is the rock in the air after you throw it up and before it hits the ground? Okay, so part E. How long is the rock aloft? So think about it. How do you answer this question? How long is the rock in the air? If I kind of redraw that, let me draw a better visual for you, and it might make sense. If I start with my throwing up of the rock in the origin, so 0, 0. Okay, so it goes up and it comes down. That might be a better representation. So this is the path of my rock, and it doesn't have to exactly look like this. Maybe it just goes almost straight up and almost straight back down. Or I throw it wide, who knows? It could be anything. But the question here is about t, but t for this part here. So this whole entire distance down there. And so if you think about it, already this was our t-axis. Instead of calling this x, it was t. This was our position or height, so this was f of t. So we're asked, how long is this going to take to go from here to here? Because that time it's in the air. So then this is one of those situations where you have to think about, how do I answer this? Well, what do I know at this moment? What do I know right here? Well, I know that this rock is back like on the ground or at the starting point. So I know that the height right there, when it's done being in the air, is 0. So these are things you sort of have to come up with, and then once you realize, oh, that's what I know about this question, then you can start answering it. So the height is 0. We have our height function, f of t. I erased it. F of t was 28t minus 0.8t squared. And we know that we want this to actually be 0, because then it's back on the ground. It's 0 when we start, but it's 0 when we end as well. So it's 0 height here and here. And then this is a quadratic equation again. This one actually factors. We can solve this one by factoring. So if I factor out a t, I get 28 minus 0.8t. So of course, one of the answers is t is 0 because of starting time. And then the other answer is the one we actually want. So we have 28 minus 0.8t equals 0. 28 equals 0.8t. And if we divide by 0.8, we're going to get that t is just about 35 seconds. And let's just double check. Does this answer logically make sense with the rest of our answers? Well, we know that it reached its highest point at 17.5 seconds. We know it was halfway down from that height at about 29 seconds. So yeah, this makes sense. 35 seconds, we're back at the ground. All right, so long question, but hopefully it gives you the idea of all these things you can do with the first and second and third derivatives. Well, we didn't really do anything with jerk, but the first and second derivatives of your function. Now, you'll come across more questions like this. The only other thing to think about is if you were to graph like one of these functions, the velocity functions or the acceleration function, and what that tells you about the position of the object. So let me sort of draw that for you, and we'll end with that example. Okay, so I'm going to try to recreate a drawing for you here. So we have our coordinate system. I'm going to go up and down 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we'll go out to 10 on our input axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Now, I'm going to draw some points for you, and then we'll connect them. So we have, looks like 0, 0, 1, 2. Let me just label these so you can copy them. 1, 2. We're going to hit 2, 0. We're going to go down to 3, negative 2. So 3, negative 2 is right here. And we're going to end up connecting these points. So connect those. Then we're going to go straight to 6, negative 2. 3, 4, 5, 6. So 6, negative 2. And then let's go up to 8, 2. This is 8. we're going to pass through right here, 7, 0. This is 8, 2. And let's end at 10, 0. Oh, I think that was, yeah, there we go, got it. 10, 0 right there. All right, so sort of just putting this drawing out there for you, and then let's see what does this represent. So let me give you that information. This figure is velocity. So this is the velocity of an object, or the derivative of the position of that object. And it's in meters per second. And it's of some object that's moving. So this y-axis, this is the velocity's output. This x-axis is actually t, or t input. All right, so some questions for you. When does the object reverse direction? Okay, so when does the object reverse direction? So think about it really quick. Let me write that down, actually. When does the object reverse direction? If this represents velocity, I sort of briefly mentioned that velocity can be negative. So velocity is positive anywhere above my t-axis, right? Think of that like x-axis. But then velocity is negative down here. This is, you have to sort of picture what this is saying numerically. This is positive velocity anywhere above this axis, and it's negative velocity below. So anytime your velocity is negative, it actually means that your object turned around, reverse direction. So here, it reversed. It was going in one direction, its velocity was increasing, its velocity started to decrease, and then right here, notice what this number is. This is 0. So it kind of makes sense that down here we just reverse directions. Think about it like maybe moving in a vehicle. If you're driving a car, you're increasing your velocity, you start to slow down, your velocity is 0 because you're making a U-turn. So you turned around, and now negative velocity just means you're going the other way. So when does the object reverse direction? Right there at 2, okay? So we'll say, let's see, part A here. Say t equals 2, and it happens again at, this is 7. So t equals 7. So it's 2 seconds after we start and 7 seconds after we've started this object's path. It moves or reverses direction. All right, let's see. Let's answer another question. When is the object moving at a constant speed? So when is, we'll just say the speed constant. All right, this should hopefully make sense just by looking. So when is the speed constant? You're not increasing your speed or decreasing your speed, it's constant. Hopefully you can tell by looking. All here, constant speed. This is -2 for your velocity. So you're constantly at a velocity of -2. So it's an interval from time 3 to time 6. So in between these two time values, between 3 and 6 seconds, your velocity is constant. All right, and so this is sort of just some of the things that you're going to think about here. I'm going to try to do one more thing with you. I want you to think about the acceleration. So let's sort of extend this to the acceleration. So let's say graph the acceleration of this object. This is the velocity. How do I graph the acceleration? Well, the acceleration is the change or the derivative of the velocity. So if I think about that, I'll be able to graph it. Let me see. I'll just actually put it right underneath here. This is our velocity. I'm going to try to copy this same coordinate system and then plot points there. So this is now going to be my acceleration axis. Let me put 1, 2, 3, 4, 5 really quick. Down to -5, and then out to 10 real fast. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, my input is still t. So graph the acceleration. Think about it. Your slope or your rate of change of your velocity is acceleration. So I know I'm saying it, but really understand this. The rate of change of velocity is acceleration. The derivative, the rate of change, the slope of velocity is acceleration. So how do I answer this? Well, I just find the slopes everywhere. So from here to here, notice I have a slope of this little patch of my line here. I rise 2 and I run 1. So the slope here is 2 over 1. So from time 0 to 1 second, my acceleration, the rate of change of my velocity is this slope right here. And it's 2 over 1, which is 2. So from here to here, my velocity is 2. So it's a constant, my acceleration is 2. So it's a constant acceleration right there. Technically, I should put open circles here because of, I don't know exactly what's happening at the ends or it's changing at the ends. So let's kind of keep doing this. From here to here, what my velocity is decreasing, okay, it goes from a lower number to 0 and then to negative. So I want to know, well, what happens from 1 to 3? And what's the rate of change? Because the rate of change of the velocity is acceleration. So I have this point here, and then I go down to this point. So I drop 1, 2, 3, 4. So I drop 4, and I run 1, 2. Okay, so rise over run. We dropped 4, we ran 2. So this is negative 2. So the acceleration, or the rate of change of the velocity, between 1 and 3 seconds is negative 2. So down here at negative 2, from 1 to 3, let me just put 1 to 3 here, is negative 2. Okay, and so I won't do the whole thing, but that's the idea, okay? Actually, let's do one more part. What happens here? What's the slope from 3 to 6? The rate of change. Well, it's not changing. It was constant, so 0. So from 3 to 6, 3, 4, 5, 6. This is constant, so this is 0. Constantly 0. All right, and you can keep going to get the rest of it. But that's the idea. So you want to just sort of think a little bit about these types of questions before you try to answer them. Think about what it represents. If I'm asked about acceleration, I have to now kind of remember that that means that it's the rate of change of the velocity, or the simple way to say it is it's the derivative of velocity. But if it helps you in real life situations, think of it as the rate of change, or slope, if that even makes it that much more clear. Slope, rate of change. So the main thing is, if your function represents position, start taking derivatives and you get other information about your function. First derivative of position is velocity. Second derivative of position is acceleration. All right, so that's it for this one. Hopefully that's good enough for you guys to feel like you can kind of handle some of these problems. They're not always about throwing something up in space, but if it's any object that's moving, you can use this idea. All right, so that's it for this one. Take care. See you next time.